Welcome back to our series on applied regression analysis. I'm Mark Ledbetter. This is lecture video 44. We are in chapter 12, part 3, the final part of chapter 12. So far in this chapter, we have studied dummy variables. Another name for that are indicator variables, which I find to be a more common reference to these variables. We talked about the rules for defining them. We said that, say, for gender, we could let z equals 1 for female and 0 for male. If we have more than two levels, say low, high, or low, medium, and high, then we cannot, for regression, have one indicator variable with all three levels. What we do is we have, if there's three of these, we'll come up with two indicator or dummy variables. And so let's say z1 equals 1 implies high. 0 is otherwise. z2 equal 1 implies medium. 0 is otherwise. Then z1 equals z2 equals 0 implies low. And that's how we define indicator variables or dummy variables. We talked about the questions for comparing two straight lines. Are the slopes the same? Are the intercepts the same? Are the two lines coincident? Are their slopes and intercepts the same? So if their slopes are the same, they're parallel. And if slopes and intercepts both are same, then they're coincident. Okay. And we talked about two different methods for comparing straight lines. There was the first method where we looked at this as two different regression models, and we did a two-sample t-test to compare or to test whether the intercepts were the same, and we said that that has a lower power, so we're going to use method 2, a single regression equation, to compare the two straight lines. And we did a test for parallelism last time. In this video, we're going to continue with a test of equal intercepts and a test of coincidence, are the lines identical, and talk about some strategies and interpretation for comparing the two straight lines. We're also going to do some examples. So let's get started. So the test of equality of two intercepts is equivalent to h naught beta 2 equals 0 versus ha beta 2 not equal to 0 in the model with x, z, and the interaction between x and z. So this is a variables added last test. So there's another approach that the authors bring up, and that's considering the variables added in order test. And they give these two models here, which is exactly what we have done before. And please notice that if we do use this method, which we will, then this assumes that the slopes in both of these equations are the same because we're using beta 1 for both of them. Okay. Now, they want to use this approach in testing this. To do so, they're going to modify the test statistic, and that's going to modify it to be more like the variables added last test. So please note that this is different than what we've done so far. So far, we would not have this in the denominator, but they are suggesting that we do that. So we're going to. And so we have SS of z given x. So we're adding gender given that age is already in the model. And so we calculate the SS, the sums of squares difference, the same, SSR of x and z minus SSR of x. But we're going to divide by the MSE of the full model. Okay. Now, we have the output in the previous video or from the previous notes here. And so here we have the variables added in order table. So for x, xz, and xz, x times z. And so we're going to take SSR for x and z minus SSR for just x. And that's what we have here. And then we take 80.2, which is the SSE of the entire, for the full model, So 80.02 is the MSE for that, and we divide by that. And before we go, that has 65 degrees of freedom. We're doing a difference between 2 and 1, and so the degrees of freedom in the numerator is going to be 1. And so when we take this subtraction and do the division, we end up with an F statistic of 38.22, with 1 degree of freedom in the numerator, 65 degrees of freedom in the denominator. And the p-value for this is less than 0.0001. We reject H naught, beta 2 equals 0. The two intercepts are judged to be different. In other words, there does exist sufficient evidence to support the claim that the slope, that the intercept beta 2 is 0, or is different than 0. So there does exist sufficient evidence to support the claim that the coefficient which is beta 2 is not 0 at a whatever percent confidence level you want to pull here to specify. 99%, 99.9%, we'll use that. Using a simple random sample of, n equals 66. Okay. Now let's talk about a test for coincidence. So we could test this using the null beta 2 equals beta 3 equals 0. So beta 2 and beta 3 are 0 versus HA beta 2 not equal to 0 and or beta 3 not equal to 0. And we're using this full model again. Okay? And so for female, this is actually for male, not female. It's reduced to this. So if Z is equal to 0, that's male, then the model, this full model, this goes to 0, this goes to 0, and we're left with this equation. So we're going to do a multiple partial F test, and we're going to look at adding XZ and Z. And we have to do them both because if Z is 1, then we end up adding both Z and XZ terms here, okay, in this model. All right, so we can't just add one of them. If we have both in the model, we have to add them both at the same time. So XZ and Z given X is already in the model. So that's the sum of squares of XZ and Z given X. And there's a difference of 2 here. So we're dividing by 2. And so we can take the SSR of XZ, XZ minus the SSR of just X and divide by 2. And from our previous table, we can see that, that we're going to take 18,010.33 minus 14,951, and that's what we have here, divided by 2 over the MSE of the full. We get an F of 19.1, has 2 degrees of freedom in the numerator, 65 in the denominator. We can compare this with the biggest test statistic or critical value that we have in our tables, F tables, so 0.999, 2 and 65, that's 7.72. And so since 19.1 is bigger than this, we can say the p-value of the test statistic is less than 0.001. Therefore, we're going to reject the null hypothesis. It says the lines are not coincident, so there does exist sufficient evidence to support the claim that either beta 2 or beta 3, either beta 2 not equal to 0 and or beta 3 not equal to 0 at a 99.9% confidence level using a simple random sample of n equals 66. Okay. The lines are not coincident. So now let's look at this strategy. Okay, so we're going to start with the full model. And the first test is that beta 2 and beta 3 are equal to 0. If we start with the coincidence test, then if it's significant, or if it's not significant, then we can conclude that they're coincident and we're done. So we've done the minimum number of testing by going in this, using this strategy. If it's significant, in other words, beta 2 or beta 3, one of those is not equal to 0, then we test for parallelism. And so if beta 3 is not significant, then if that's non-significant, then we said that beta 2 is basically not 0. So we consider that they're parallel but not coincident lines, and we're done. If it's significant, then we'd say that beta 3 is definitely equal to 0. Now, the only thing that could be is it could be that beta 2 is equal to 0 or not. So do we want to test for equal intercepts? And if we do, then we test that beta 2 is equal to 0, and we use a variables added last test here. And if it's not significant, then they're not parallel, okay? And we're done. If it is significant, then we conclude that they're non-parallel lines with non-equal intercepts. Okay, and so then we're done. So if we apply this strategy to the age systolic blood pressure data that we were just working with, we arrive at this equation, meaning that the two lines are parallel but not coincident. Now let's do problem 8. It says in problem 1, separate the straight line regression of SBP on QIT. Separate straight line regressions of SBP on QIT were compared for smokers and non-smokers. Smoke equals 1 for smokers, smoke equals 0 for non-smokers. And this data is from problem 2 in chapter 5. And so we do see that we have the type 1 SS here. And this will be handy. So we want to define a multiple regression model that uses both the smokers and non-smokers, and that defines straight line models for each group with possibly differing intercepts and slope. Okay, and then it goes on to say something that might be confusing because it's really, I don't consider it very necessary. Define the intercept and slope for each straight line model in terms of the regression coefficients of the single regression model. I guess that is important because we want one single model. So this is the model that we come up with. So we have QIT, smoke, QIT times smoke, the interaction, and smoke equals 1 is a smoker and 0 is not. Okay, so if it's smokers, then that means that smoke is 1, and so this term becomes beta 2 times 1, or beta 2, and this becomes beta 3 times QIT. And so we have beta 1 and beta 3 that can be combined, and beta 1 plus beta 3 will be the slope. And then we could combine beta 2 and beta naught into the intercept. So that's what we see here. If there's non-smokers, then both of these terms with smoke in it go away. So we end up getting rid of this term and just end up with beta naught and beta 1. Okay. So we want to use the accompanying computer output and determine or plot on graph paper the two fitted lines obtained from the fit of the regression model. So we're going to use these two equations, and so we take beta 2 and beta naught, and so we find beta naught and beta 2, and we add those together, and that's 79 something, and that's what we end up with here. And then we're going to take beta 1 and beta 3. So we take beta 1 and beta 3, add those together, and we're going to get around 20. And that's what we have here times QIT. And then for non-smokers, we have just beta 0 or beta naught and beta 1. And so those is going to be 49 point something and then 26.3. That's what we see here when we plot them. It does not look like they have, that they're parallel, and it doesn't look like they have the same intercept, okay? So, but that's just this random sample. So let's test statistically, is that deviation from parallel significant or just a random chance based on the sample, okay? So we're going to test the null hypothesis that the two lines are parallel, and then we're going to test that they're coincident. So we're doing this in the reverse order of the strategy they just set out for us. So I find that interesting. Okay, so we want to do these tests. So for each of these tests, state the appropriate null hypothesis in terms of the regression coefficients of the regression model. All right. So the test of parallelism is H naught beta 3 equals 0 versus H naught beta 3 is not equal to 0 in the model here. Okay. So now, if beta 3 is 0, then this term goes away, right? And so if beta 3 is 0, then the slope is beta 1. The slope of beta 1 for QIT, okay? If it's not equal to 0, then the slope is beta 1 plus beta 3. And then we would not have parallel lines. So we're going to use an F-test for adding smoke and QIT to the model with smoke individually and QIT individually. So the interaction, we're adding that. And so this is basically a variables added last test, and we can get the SS of QIT interaction with smoke given QIT and smoke are already in the model. So from the SS1 table, we can get this directly. They have done this as if a very convoluted manner with the data that we're given. So 4184, and then what they've done is they've taken this 4184 here and they subtracted these two values added together, which of course is going to give you this value here. So I would just choose that value, and then they want to use, we use the full MSE, the full model MSE, and that's just 80.0664, and so that's how I would do it with this data. They have gone, like I said, kind of convoluted. You get an F value of 0.796, which is small. It's close to 1, and so, but below 1. So we have 1 degree of freedom in the numerator and 28 in the denominator. The p-value is 0.38. So at any realistic alpha level, we do not reject H naught. So there does not exist sufficient evidence to conclude that or to support the claim that the two lines are, there does exist sufficient evidence to support, or no, we do not reject, so there does not exist sufficient evidence to support the claim that the slopes are, that beta 3 is not equal to 0 at a 95% confidence level using a simple random sample of n equals 29. Okay. So remember that the test of coincidence is the same as testing that both beta 2 and beta 3 are equal to 0 in this model against either one, beta 2, not equal to 0, and or beta 3 not equal to 0. So we have tested that beta 3 is equal to 0, and we've said, yes, do not reject H naught. So with that, since this is either or, we are now basically, since we know that beta 3 statistically is not different from 0, then we're basically left testing beta 2 is not as well. But but that's not all this test does, right? We already know the beta 3 is close to 0, so is beta 2 close to 0 as well? All right, so we're going to do the F test. We're going to add both smoke and QIT to this, and so we need SS of smoke and the interaction given that QIT's already in the model. So there's a typo here. over the MSE of the full model. So again, the MSE of the full model is 80.0664. And instead of using their convolution, I would like to show you that I just added 582 and 63 from this table. Because remember, the sums of squares type 1, they're additive. So I just simply took these two and added them together. And I get the sum of squares for adding both of them to the model, right? So that's good to know. Makes it a lot easier than what they're doing here. And then we have 2 degrees of freedom in the numerator and 28 in the denominator. And when we look up 4.035, we can go to the different F tables. And if we look at the 0.025, the critical value at 0.025, we'll see that this value will be smaller than that value corresponding, but it will be larger than this one, and so we know that the p-value is somewhere between 0.025 and 0.05. If alpha is equal to 0.05, we will reject H naught, and we'll say that the two lines are not coincident. In other words, the intercepts and even though they're parallel, the two lines are concluded to be parallel, they're not coincident, so their intercepts are not the same. So there does exist sufficient evidence to support the claim that either beta 2 or beta 3 are not equal to 0 at a 95% confidence level using a simple random sample, or tested with a simple random sample of size n equals 29. All right. Please don't forget to scan your lecture notes by midnight, the date listed on the course calendar. If you have questions, come to virtual office hours. If you need an answer before you can make it to virtual office hours, then by all means email me, but I need you to send me 2 things. 1, the picture of the problem, because I may not have it with me, and 2, the picture of your work so far so I can see your approach to this problem and help you through email efficiently. Please take care of yourself, and we certainly hope to see you next time.